Now let's talk about odds and risk. First, risk is the probability that something will happen. In our previous example, the risk that a black person would be sentenced to death was about 18%, or 95 divided by 520. The risk that a non-black defendant would receive the death sentence was about 13%, or 19 divided by 147. The risk ratio is the ratio of one risk and the other. In this case, 0.183 divided by 0.129 equals 1.42. Therefore, we know that the risk of being sentenced to death is 1.42 times higher for black defendants compared to non-black defendants. The dividend changes when we look at odds. Using the same example, we would take the number of black defendants sentenced to death and divide by the number of black defendants not sentenced to death. The odds in this case are about 22%, or 95 divided by 425. The odds for non-blacks are 15%, or 19 divided by 128. We can now create an odds ratio dividing the odds for blacks by the odds for non-blacks. Dividing 0.224 by 0.148, we get 1.51. In this case, we can say that your odds of being sentenced to death are 1.51 times higher if you are black. As I noted, at the bottom of the slide, we're more likely to use an odds ratio because risk ratios cannot always be performed, especially with low frequency events. It's important to know how we would write up the results of our statistical analyses. Depending on the journal and type of science we're doing, the way we write up the results may differ. However, reporting the results usually includes the same components: citation, problem, approach to the problem, where and how we collected data, how many observations there were, unconditional probabilities overall and by race, conditional probabilities, odds, risk or odds ratio, drawing conclusions, and putting the study in context of other relevant work. Take a couple of minutes to read through this write-up. Is it clear to you? Are all the components included? You may want to pause this. Moving on, let's go back over discrete and continuous variables. The distributions of these two kinds of variables are treated somewhat differently in probability theory. With discrete variables, we can speak of the probability of a specific outcome, but with a continuous variable, we need to speak of the probability of obtaining a value that falls within a specific interval. Remember that a discrete variable is one that can take only a countable or small number of different values, whereas a continuous variable is one that can take on an infinite number of different values. What if we had 25 M&Ms of each of 4 colors? We drop them all into the same bag. The probability that we will draw exactly one blue M&M is 1 divided by 4, or 25%. Now let's think about the weight of an M&M. Now they don't have very much in weight, but I doubt that they are all the same weight exactly. Here we have an example. What is the probability that an M&M will weigh exactly 1 gram? It is infinitely small, but there is some reasonable probability to think that the weight will fall in the interval between 1 gram and 1.25 grams. Notice the difference between what we can talk about with regard to probability for discrete variables versus how we talk about probability for continuous variables falling into some interval rather than a specific event or value. Now look at the plots of data for discrete variables and continuous variables. Notice how differently they must be represented. Proportions for discrete variables translate directly to probabilities. What is the probability that a person chosen at random will agree that his or her health is close to ideal? When thinking about the probability of a continuous variable, it's ridiculous to think about the probability of any specific outcome. Rather, we would be interested in the probability that a woman would give birth around a time period or during an interval. While the plot doesn't give us enough information to calculate the exact probability, it's clear to see that the probability of having a baby around 20 years of age or 25 is much higher than 15 or 40. As we prepare to discuss sampling distributions and hypothesis testing, let's look at some concepts from previous chapters. Sample statistics refer to mainly the mean and standard deviation computed on a sample. Population statistics are also referring to the mean and standard deviation, but of a population. It is the number of observations in a sample. Conditional probability refers to the probability of an event occurring given that some other event has occurred. Now, before we continue, think back to the first day of class, and I separated you, if this was a face-to-face class, into two groups of supervisor and employee and asked your height. I planned ahead. For today, as the book says, there's a lot of evidence in the literature that taller people tend to be more powerful than shorter people, with higher salaries, higher status, etc. The study in the book looks at the situation backward, asking people to report their height after they've been told that they will play the role of a supervisor or employee, just as I did to you. High power group overestimated their actual height by 0.66 inches, while those in the low power group underestimated their actual height by an average of 0.21 inches. While we would expect the two groups to differ a tiny bit, this is a difference of more than 3/4 of an inch, more than a tiny bit, attributable to chance? With statistics, we can answer this question. As an aside, I'll point out that Napoleon was not as short as we were led to believe. He was about 5'6". Next,